Hello everyone, my name is Weihuang. Today I will present the work reliability of GAN-generated data to train and validate perception systems for autonomous vehicles. This work was done with Nasim Souly and Pratik Brahma while I was an intern at the Volkswagen Group Innovation Center at California. In autonomous driving, we collect huge amount of data using different sensors in common scenarios. However, there are many real-world scenarios that either do not exist or exist in smaller quantities in finite datasets. This is often referred as the Longtail Problem. For example, the people running across the highway or the animals blocking the road. The typical solutions to tackle with corner case scenarios are collecting more corner case data in real world or generating real data using simulation. We can also restrict the operating domain when real scenarios happened. Generative adversarial networks have come up as an interesting alternative to generate real-looking data. GANs with other perception modules can be used to achieve several different functions such as addition, where we can, for example, create a long-tail situation by adding a child in the middle of the road. We can also achieve the deletion, where we are able to remove objects from the scene and realistically fill it with the background. We can also edit the shape of the objects. For example, we have a one-to-many modules to come up with various shapes and structures of road objects and traffic agents using a user-friendly interface. We can also change the motion and behavior of the agents. For instance, we can simulate imagery for scenarios with different types of motion patterns of traffic agents, such as sharp cutting. Last but not least, the style transformation. We can transfer imagery from one domain to another domain, like the daytime to the nighttime. In this work, we aim to thoroughly study the usability and reliability of GAN-generated data to tackle with long-tail situations. Here are two questions that we would like to answer. First, can we use GANs to simulate corner cases for training perception modules? For example, we train an object detection model on GAN-generated night images to detect pedestrians at night. Can it perform well on real night images as well? Second, can we rely on GAN data to validate advanced driver assistance systems instead of real-world data? For example, if we can conclude with high confidence that the self-driving software is unable to detect GAN-generated Halloween costumed pedestrians, and the same conclusion also holds on real-life pedestrians with such costumes, then it would be indeed a life-saving way of doing function validation. To answer these questions, we generate out-of-distribution or corner case data from normal data using GAN generators and then test it on downstream perception as shown in this figure. The solid line shows the pipeline for training and generating data using GANs, and the dashed line shows the follow-up testing and evaluation in the downstream perceptions. Specifically, we evaluated GAN data in two tasks. The first one is object detection application, where we consider daytime imagery as normal data and nighttime imagery as corner cases. We used CycleGAN to generate images in night domain and trained a ULV5 model to evaluate object detection performance with different combination of real imagery and GAN-generated imagery. The second task is a sharp cut-in scenario classification application, where we consider normal driving videos as normal data and generated sharp cut-in videos as corner case data. Then a classification module based on CNN and LSTM is trained to detect sharp cutting scenario from normal driving scenario. We run each experiment multiple times to get statistic results on accuracies. Since we cannot find a public dataset that has all the features we need, we collected a dataset with high-resolution RGB camera imagery, LiDAR, and vehicle bus data by driving on California highways. The sample RGB images is shown on the left. We annotated 3959 discrete images with instance-level semantic segmentation masks. We generated bounding boxes for different objects according to this segmentation mask as well. We also annotated 600 short video clips based on the type of scenario like changing lane or sharp cutting. The dataset is also meta-annotated with tags like weather, road conditions, and etc. In object detection application, we first converted daytime images into night domain. To improve the quality of generated images, we applied different techniques such as transfer learning, random cropping, and full resolution inference. Here are examples to show the improvement for each technique. This is an example of day-to-night translation using the trained cycle GAN. The details of objects were preserved in the night domain. Those night images were used to train a YOLO-V5 model for our task 1, that is the object detection. We trained a YOLO-V5 model with different combination of real-day images and various amount of GANnet images. For testing, we compiled two test sets. One had 148 real-day images, and the other one had 148 night images. I have to mention that the number of objects is highly imbalanced in our dataset, where cars are way more than the motorbikes. We also did multiple experiments to see whether these conclusions are statistically significant. This figure shows the MVP value on the test set with real net images. As we kept adding GANnet images in the training set, the MVP values on real net images kept increasing. Also, adding real net images and adding same amount of GANnet images have similar results during the inference. Here are predicted bounding boxes on a sample RealNet test image. We compared one model trained with real day and a few net images with another model trained with real day and GAN-generated net images. Also, we had no motorbike objects in the RealNet training set due to the limited images. As you can see, the model trained with RealNet images cannot detect motorbikes in the test set. However, GANnet images had some motorbikes because they were transformed from the real-day images. We noticed that model trained with GANnet images could capture features of motorbikes and detect them on test set with high confidence, which helped a lot in the zero-shot learning scenarios. To help the CycleGAN model generate data specifically for downstream object detection network, we would like to put more weights on the objects of interest instead of background, such that the generated images could reserve more detailed features on objects. We modified the original CycleGAN loss function by adding more weights on the objects and less weights on the backgrounds. We got the overall MVP improved from 0.445 to 0.455. We also explored if we can use GAN-generated data to validate the object detection module. For this set of experiments, we trained YOLO-V5 models with real-day images only and tested on either 148 real-net images or 148 GANnet images, which converted from real-day test images. The MVP values are shown in the table. Although overall MVP values remain in the same range, class-wise average precision varies a lot. The model trained solely with real-day images was not expected to behave well in the night domain. One such adverse pattern was that the truck either not being properly detected or only its lower half being partially detected as cars in the night domain. This is probably due to the fact that only the lower part of such bigger vehicles are illuminated by the front lights of each vehicle. But interestingly, we could see the same pattern of errors on GAN-generated testing data too. We also evaluate GAN-generated corner case at the video level for scenario classification application. Specifically, we would like to detect the sharp cutting of a vehicle by hastily changing lanes into the ego lane in front of the ego vehicle. We trained Deep Lab V3 model for semantic segmentation and mask RCN for instance identification using the instance level semantic segmentation annotations. Then we leverage Unity 3D game engine to manipulate segmentation maps. We use the calibration parameters of the real camera to mount a similar virtual camera in the simulation and use the data from the vehicle bus like GPS location, acceleration to design the roads and ego vehicle motion in the simulator and generate a sharp cutting behavior. This is then used to manipulate the actual segmentation masks. We then used the Pix-to-Pix HD to generate the realistic video frames for the intended cut-in event and normal video clips. This is the zero-shot setting since we have no sharp cut-in videos in the training set. To perform video action classification while maintaining a low computational cost, we use the popular CNN plus LSTM model that applies the LSTM on the feature space obtained by convolutional network on a sequence of video frames. To remove the potential bias on GAN-generated data, we compile the real normal videos, GAN normal videos, and GAN sharp cut-in videos as training set. Again, as a reminder, this is a zero-shot setting since we have no sharp cut-in videos in the training set. We achieved 76% accuracy with 0.88 precision and 0.66 recall in this zero sharp cut-in detection when tested on real normal and real sharp cut-in corner cases. In summary, we empirically studied whether one could rely on GANs to generate data for training and evaluating vision-based perception models. With our experiments on domain translation, we demonstrated how including GAN-generated out-of-distribution data could substantially increase the performance of downstream modules in object detection applications and scenario classification applications. We also uncovered and suggested mitigation techniques for the bias when GAN-generated data is introduced during training. Although results were inconclusive on whether one could quantitatively validate perception models by testing using GAN data only, we showed interesting detection patterns that also occurred when tested with real data. Please refer to our paper for further experiments and results. With this, I would like to thank you all for attending this presentation, and I would like to take any questions.